There is a very special matrix in matrix algebra called the identity matrix. And the identity matrix plays the same role in matrix algebra that the number 1 plays in scalar algebra. You know, if you multiply any scalar by the number 1, you get that same number back. 1 times 3 is 3. 1 times 5 is 5, etc. I remember going over flashcards when my kids were little. Remember, I don't know, did you ever have these flashcards when you were learning your multiplication tables? And they would have those in there, 1 times any scalar. It gives you that same scalar back. Well, the identity matrix is like the number 1, but it applies to matrix multiplication. A 2 by 2 identity matrix is just this. Oh, the identity matrix, of course, is always square. And a 2 by 2 identity matrix is simply this. 1, 0, 0, 1. It has 1s along this principal diagonal. The off-diagonal terms are 0. Okay. So sometimes this is written as I sub 2 to let you know it's a 2 by 2. The identity matrix corresponding to a 3 by 3, I sub 3, is just this. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. I sub 4, you would now have a 4 by 4 matrix. All of these terms would be 1. All the off diagonals would be 0. Let's just verify what I said earlier. Let's take the 2 by 2 identity matrix. If you multiply this times any matrix, you'll get the same matrix back, so long as the two matrices are conformable for matrix multiplication. Okay, so let's just make up. Let's make up a matrix over here. Now, in order for matrix multiplication to be defined, how many rows are we going to have in that lag matrix? Yeah, 2, because these two inner numbers have to be the same. This I is a 2 by 2 here. So if you have some other matrix A would have to have 2 rows. It doesn't have to have 2 columns. A wouldn't necessarily have to be square, but it would have to have 2 rows. Let's just assume A is also a 2 by 2. And let's arbitrarily pick a 2 by 2. Somebody give me a number here. 7. All right, another number. 4. Another number. 6. Another number. 9. Okay. Now, let's do this multiplication process. If what I've said is true, when we perform this multiplication, we should get what matrix back? Right, exactly. So let's just verify that this works. Multiply the first row, and it'll also give some more practice in doing multiplication. Multiply this first row times the first column. What do you get? 1 times 7 plus 0 times 6, or 7. See why this has given you the 7? Because the 1 hits the 7, then the 0 hits the 6. But since the 0 is hitting the 6, this will just drop out. So that's why you get the 7 here. Multiply the first row times the second column. What do you get? 1 times 4 plus 0 times 9. Of course, the 0 is going to make this one vanish, so you just get a 4. Now we move to the second row. Second row times first column gives us what? 0 times 7 plus 1 times 6 is just 6. So now it's going to give you this element right here. And then second row times second column gives you 0 plus 9, or just 9. Okay. Actually, in this case, what we are doing, we are pre-multiplying A by the identity. But it also works if you do the multiplication the other way. If you calculate A times I, you would see in this case you also get A. So whether you pre-multiply the matrix by the identity or you post-multiply the matrix by the identity, you get the same result. Okay, you just get A back. So the identity is like the number 1, in other words. There is also a matrix in matrix algebra that corresponds to like 0 in scalar algebra. The only difference is now it's called the null matrix. The null matrix is just a matrix of zeros. A 2 by 2 null matrix would just be this: 0, 0, 0, 0. Obviously, if you multiply the null matrix times any other matrix, what are you going to get? 0. Yeah, the null matrix, in other words, yes. You get the null matrix back. So the null matrix is just like the 0 in scalar algebra.